Okay, tracks 2 and 3 were just two little, 4-minute videos that show kind of the cool effects of air, of how air affects um, the basketballs, the tennis balls, and things like that. And we don't take those into consideration for this course. So when we're doing projectile motion, and this is when we're under the influence, means the acceleration is under the influence of gravity alone. Here is one of the most important slides that I'm going to beat this into your head. Remember how when I did that problem where they showed the airplane moving, we dealt with the y coordinates and the x coordinates, right? In that problem, we actually had an x coordinate. We actually had an x component of velocity. In projectile motion, since we are eliminating the Magnus effect, since we're eliminating all of the other drag effects that air can cause, that our atmosphere can cause, there is no other, and in fact, there'd be an acceleration in the z direction too. But there are no other, there is no acceleration in the x direction. None. So that means when I launch something, the x component of its velocity, since it experiences no acceleration in the x direction, it stays constant the entire time. It stays constant the entire time. Okay? That's huge. That is a huge thing to know. I mean, that's like beyond huge. That's like, it'll piss me off if you don't learn that. No, I'm kidding. All right, so anyway, so look what happens here. Here's an airplane is moving horizontally with a constant velocity of 115 meters per second. Now notice what happens at an altitude of 1,050 meters above the ground. Determine the time required for the care package to hit the ground. I'm going to do two things with this problem. I'm going to do two things. Now notice, the airplane is staying in a nice vertical motion, and it's flying at a constant speed, at a constant velocity of positive 115 meters per second. So it's going 115 meters per second here, 115 meters per second here, 115 meters per second here. Guess what? The package, the care package that it's dropping here from 1,000 meters in the air, okay, the care package is driving from, when I was in the Marines, when I was a young scrappy lieutenant and was into adventurous things, I was with Landing Support Battalion, and I was the air delivery platoon commander for a while. And so we dropped a lot of stuff out of the back of airplanes and helicopters and things like that. And we got to jump every once in a while too, so that was fun. Anyway, but notice, the package stays underneath the aircraft the entire time because it's going 115 meters per second here. Guess what? It's also going 115 meters per second in the x direction here, and it's also going 115 meters per second in that direction when it hits the ground. And we talked about the other day in class, right when it hits the ground, it's still going 115 meters per second in the x direction. But look at this y component of the velocity. It's getting big, big. Why? Because that's where the acceleration is taking place. Okay? And so the total acceleration is this total velocity is this huge velocity vector coming this way. So I'm going to write down this information. And what we're going to do is I'm going to break this into two parts. We're going to figure out how long it was in the air. Then we're going to calculate the final velocity that it went. And we're also going to determine how far it went this way. Okay? So what are we doing here? Here's what we're doing. Here's what we're going to do. We're going to do this. We're going to calculate for the airplane problem. Airplane. A-plane. Talking like my 2-year-old granddaughter. A-plane. All right, airplane problem. All right. We know that the package had an initial velocity in the x direction of 115 meters per second. I know that the acceleration in the x direction is equal to 0. And I also know that these are the stuff I know in the y direction. The initial velocity in the y direction is equal to 0. I know that the initial I know that the acceleration in the y direction is equal to negative 9.8 meters per second squared. I know that the height that it was dropped from, was 1,050 meters. Okay, so the height is 1,050 meters, and I know this, so I know that the height is 1,050 meters, and I've got to figure out the time. And then the other thing so I need to find the time, and the time is the same over here too. These two times are going to be the same because it's the package. It's not like in two different universes. It's the same. All right, and I want to find the range too. I want to find the range of this package, and the range is how far it went this way. It's displacement in the x direction. That's the range, okay? And that will be v naught x times the time that is in the air, all right? So that's what we're going to do. Let's start with the time one first, and then we'll stop and then finish the problem, okay? I don't know, can you all see my screen? It's probably recording the entire screen. It's 12:38. I'm hungry. I'm gonna eat some lunch. But anyway, first we're gonna figure out this problem. All right, we're gonna figure out how long is in the air. Time. Find time in projectile motion. Need to work in y-axis only, because that's where the acceleration hangs out. All right. So things that I know in the y-axis: v naught y is equal to 0. Y final is equal to 0. Y initial is equal to 1,050 meters. Okay? So I have this equation. It's just like the x equation for distance. I have this where y final is equal to y initial plus v naught y minus 1/2 ay t squared. Now, why did I say minus? Because I know that the acceleration is equal to negative 9.8 meters per second squared. I forgot to write that in up here. All right? So here we go. 0 is equal to 1,050 meters plus 0 minus 4.9 t squared. Now, where did he get the 4.9? Because I took 1/2 times 9.8, and that gives me 4.9. All right? So I've already taken care of the minus. Now, this becomes a pretty easy problem to solve, right? There it is. Oops, there it is. Look. So add 4.9 t squared to both sides is equal to 1,050 meters. Divide both sides by 4.9. T squared is equal to 214 meters seconds squared. Because look, this is 4.9. This 4.9 is in meters per second squared. So when I divide this by meters per second squared, when I divide by the acceleration, look at the units here. This is what I'm talking about. Because I'm taking 10,000 meters and dividing by 4.9 meters per second squared. So therefore, the meters cancel here and the second squared goes up there. So that's what I'm left with. Take square root of both sides. 14.6. There you go. That's how long is in the air. Now, look at this. Let's go back here. Look. The range, v naught x. I can find the range. So the range, we got that knocked. The range is equal to v naught x times t, because the x never changed. So how far that went in the x direction times 115, boom, 1,683 meters. There's the range. Hey, wait a minute. What about the final velocity in the y direction? Oh, what is the final velocity in the y direction? Final velocity in the y direction, v final y is equal to v naught y. Do we know that? Yeah. Minus g times t. Right? Because that's the acceleration times time. Or ay times, or v final y minus v naught is equal to v naught y minus ay times t, where we said ay was equal to g. So we've got v final y is equal to 0 minus 9.8 times 14.6. So the final velocity in the y direction is going to be negative, right? Isn't that what they showed us? Not the picture? Wham! And it's huge, it's big. 9.8 times 14.6 is 143 meters per second. 143, yeah, right, almost right on the nose. 143 meters per second. So the first thing I always get is the time on these problems. And then we'll look at double when I get back from lunch. Out here.